Welcome back to the classroom. My name is Mr. Wong. We are covering Module 4, Electricity and Magnetism. Inquiry question 3 about magnetism. So we're going to be focusing on these two particular dot points for today. So the aim of our experiment today, or not experiment, our lesson today, is to depict magnetic fields. We want to firstly look at how can magnetic fields be produced by electric current. We also want to be able to identify the direction that the magnetic field is going when we introduce a thing called the right-hand grip rule. So let's have a look. Okay, so as you can see, the dot point we're looking at is we're trying to apply some models to represent qualitatively and in descriptive words, that is, and describe quantitatively the features of magnetic fields. Okay. So you can see sort of the magnetic field structure. It's very similar to what you can see of 2-point charges in an electric field. So 2-point charges, you can sort of see that with the magnetic field. They do behave slightly differently for when charged particles interact, so keep that in mind. In the sense that with magnetic fields, it always goes from north to south, so keep that in mind. And the idea is very similar that the closer you are to where the actual magnet is, the stronger the magnetic force will be as well. Okay, so what we can probably show is a magnetic field simulator that represents the strength of the magnetic field. Okay, so if we look at our actual magnet, as I move it around, you can see it actually causes the fields around it to get a line in a particular orientation. So remember, the idea is it always goes from north to south. That's the idea. You can see also where the pole is, where the actual magnet is. You can see the, in terms of color contrast, the middle section of the magnetic fields are a lot stronger in their color contrast, and it gets sort of dimmer as we go further and further away. That just represents to us that as we move further and further away from the magnet, the overall strength of the magnetic field also diminishes. Okay, so, let's have a look. So, let's just quick revising on magnetic fields. Obviously, the last time you probably would have done anything related to magnets is probably around like year 8, so there's a couple of years of catching up and looking at what's happening. So firstly, we want to identify the poles in each part of the magnet. Let's start with this one on the left here. We can see, remember, the idea is it's always from north to south, so that should give us an indicator of where the different poles are. So U here is going, or this example here, it goes from U to X, so U is our north pole, and then S is our south pole there. Same idea, Z is our north pole, Y is our south pole. Okay, so that's how we deal with that. Alright, so when it comes to examining the north poles, or magnetic fields, they're quite similar when we look at point charges and their electric fields. We kind of draw them in a very similar manner. Okay, you can see our charges here, our magnets here, and our charged particles here. The way we kind of draw it is quite similar in sort of this radial form of that. So when it comes to drawing magnetic fields, just remember, you always draw it from the magnetic north to the magnetic south, and it goes in sort of this radial structure here. So radial structure. So I'll just write that down somewhere. So it's sort of a radial shape in terms of the field when it comes from one bar magnet to another. We also know that if the fields are different from each other, so if we have two different poles, they will form an attraction. So you show that the lines join together. So to show that they attract, our magnetic field lines join together. So that's the way it will go. we have how to determine the magnetic field strength. So it comes down to counting the amount of magnetic field lines, or what we call flux. So flux is a term we use in physics to measure the number of magnetic field lines passing through a given area. So let's say we box this point here, and we box this point here. Okay, we can see that at this point here we have more flux, which means that the magnetic field strength, so magnetic field strength is stronger. And then over here, our B strength, or our field strength, is weaker. Okay, that's how we kind of determine whether or not we're dealing with a strong field or a weak field. Now, how would we represent this diagram if magnetic fields were to repel each other? Now, firstly, if you have, in order to have magnetic fields repel, you need two of the same poles. Okay, so the poles need to be the same. In this case, we have two north poles, so that's what we have. Now, you can see at the middle here, we sort of have a null point. You can even draw it like an asymptote. So this null point here is where you would experience a position of zero force. So just so happens here at that little point here, there should be no force felt apart. When you're drawing the magnetic fields for repulsion, remember the magnetic field lines do not connect. So when it comes to showing or demonstrating repulsion, so to demonstrate repulsion, the field lines don't touch each other at all. So you can see sort of what we mean by, if I just draw a line through, you shouldn't be able to witness the lines getting into that touching contact. Okay, next one is, what if we have a stronger magnetic field than the others? So over here we have double in terms of the strength of the magnetic field, and we have the single one here. Well, you simply have to draw twice as many magnetic field lines. So if the magnetic field is twice as strong, then you need twice as many magnetic field lines to represent the difference in magnetic field strength. So that's what you see here. Now, obviously, when it comes to magnetic fields, there's nothing more famous than the magnetic field that surrounds our planet. For those who didn't know already, our magnetic field actually helps us block off some solar wind. So that actually keeps us safe from the radiation emitted by the sun. And it's also part of the reason why we get auroras. Alright, next part we want to see is we want to use the magnetic fields to model qualitatively the direction and strength of the field lines in current carrying wires and solenoids. So we actually have this example here with a current carrying wire, and then you can actually hopefully see that the needles do rotate a little bit, and that just shows when we have an electric current going through the conductor, you can actually generate a magnetic field around that conductor there. The video for this will come along at some point later on, and then you can actually see the actual demonstration with your own eyes. Okay, so the person who actually looked into it was called Hans Christian Ørsted. I'm not really sure how you pronounce it correctly. I'm horrible pronouncer, so I do apologize. He demonstrated that if you have a electric current flowing through a wire and any kind of conductor, the current caused a nearby compass needle to change direction. Obviously, if you recall, a compass needle helps direct the magnetic field direction. So if that needle was to flip when a current was turned on, that would probably represent that the current is generating a magnetic field. You can actually do an experiment quite simply by surrounding some magnets around an electric conductor and then turning it on and see if it causes the needles to flip. That's a really nice way of doing it. It's actually a way of predicting where the needles would rotate and also where the current could be depending on the magnetic field you generate. Okay, so that's actually what we're going to lead into. We're going to look at how to represent magnetic field lines going through a straight line conductor and also through a solenoid. So we have our straight conductor here, so our straight line conductor, and then we have a solenoid. Now, just so you know, solenoid is essentially just a series of wires, so a series of wires rotated in a circular shape, or rotated in a circular path. Okay, so it will have its positive and negative sort of component ends, but essentially everything is rotated in a circular path. Okay. Now there's quite a few things to take into account. Firstly, it's the right-hand grip rule. Now just remember the right-hand grip rule is not a stated law, it's just a guide point in identifying the direction of the current. So guideline to help you find the direction of current and direction of the magnetic field. More specifically, when we talk about current, we're assuming it's a positive flow of charge, so just keep that in mind. And one of the notations we will be using are these crosses and dots. So these crosses represent magnetic field lines going into the page. Literally, if you have your fingers right now, you're pointing directly into your screen right now. And then the dots represent out of the page, so you represent that by your fingers almost literally popping out into your face. In that way. So we're going to try and represent that in terms of the wire, and we're also going to look at that in terms of the solenoid. Your right hand grip rule does change slightly if you're using the straight conductor and also the solenoid, so keep that in mind. Okay, so the first thing is for our solenoid, your right thumb, and you can actually try and picture this by holding up your hand with me. So with your right hand, put it into a little grip. Okay, your thumb that you're looking at right now, that is going to be the direction of the North Pole in a solenoid. So for this circular kind of structure here. Okay, your fingers will be the indicator of where the positive current will be flowing. So in our example here, if you picture, you have your North Pole pointing to the left hand side. So if you grab your hand, your right hand that is, and your thumb is pointing to the right hand side, you can almost imagine your fingers sort of latching on to the solenoid. Okay, you hold it up and your fingers are pointing upwards. So in this trajectory, we can see that the current is going up and going in this sort of direction here. So we'll expect the current to sort of go in a clockwise rotation around. So that's for a solenoid. The right-hand grip rule for a straight conductor changes slightly. The main thing is you just swap the direction of the current and the magnetic field around with different components. So your thumb now is the direction of a positive charge current, or conventional current as they call it, and your fingers become the direction of the magnetic field. Okay, so assuming that my current is going up in this direction here, your thumb, your right thumb that is, should be pointing up. Your fingers are, in a way, if you have a look, is rotating around in a anti-clockwise direction. So your magnetic field in this orientation is anti-clockwise. Okay, so make sure you know the difference between the two because it can jumble up in between. Okay, if we look at this example here, imagining we have a solenoid example, or it could be a straight line conductor, it doesn't really matter. our conductor, we see this X here. That represents that the current is going into the page. Remember, if it's one, so if we only have one cross or dot, generally that means we're looking at the current. If we have multiple crosses, multiple dots, most likely you're dealing with is the magnetic field, which I'll call the B field, because that's the symbol that we use. If you have a look, point your thumb in this diagram that we have here, point it into the page, your right thumb that is, and then you can actually see, if you curl up your fingers, you can see it's rotating clockwise. Now if it rotates the other direction, you're probably using your left hand, or you have incredibly flexible fingers. I don't know which one, but not the right way. Okay, so let's have a look at this question here. We have a straight line conductor, and we want to predict the direction of the magnetic field in all these different scenarios here. Okay, so predict the direction out or in, north, south, east, or west of the magnetic fields at each point going along like this. Okay, all right. Okay, so, and as we indicate, north is this way, south is that direction there. Alright, so using the first example we have here, this is for a straight line conductor, so that's assuming that this current is going upwards. So your fingers pointing up, your fingers curl around the conductor. So if I imagine I'm sort of latching on to this arrow here, my fingers are going into the page here, and my fingers are pointing out the page in this direction here. So at point P, we have out of the page B field direction there. If we're looking at this here, our current is going in this direction, so my right thumb is going to the right. I'm going to grab onto the arrow. So in the side of Q, we have my fingers pointing into the page, and then on the side of R, we have fingers pointing out of the page there. If we look at A, our current is going into the page, so that essentially what that means is my hand is being gripped, my hand is rotating clockwise, so I'll experience a magnetic field that's rotating in this orientation here. And then in this example, this is coming out of the page, so I'm experiencing the magnetic field rotating anti-clockwise in this direction here. Okay, so that's what we get. You can therefore work out the direction. From T to A, it's southeast, and then from S, we'd have directly south. So find the tangent of the line. So if we have a look, A to T, so for T in particular, if we draw out a tangent line to where it is to A, we can see that that is southeast, and then if we draw the tangent line of where south, or S here is, lines up with our charge or our current, it's going directly south there. Alright, let's compare the pair. What difference do we see here? Well, if we actually compare the current, we can see that T would have, so T has a higher current, and S has a lower current. Okay, how do we know that? Because we know that the lines are a lot smaller. So two currents carrying, compare the currents, that's what we see. The diagrams have been drawn incorrectly. What are the errors that we see here? Okay, let's sort of have a look. Okay. Oh, also, the other thing I didn't mention as well, we can also see that the current in this example, if we're looking at this dot here, is coming out the page. So out of page, and this one is also out of page, like so. Now if we try and compare the two, we can see that the issue, so there is an issue, and that's the field lines are equally distanced. Now why is that an issue? Because remember, we always said that the center point almost acts like a point charge. So the center point has the strongest field strength. Which means that the field lines should gradually be more, spread out. So field lines should be more spread out as you go further out. So what exactly should we see? We should see perhaps this line here, and then it gets a bit broader out here, and then it gets even more broad out like so. Obviously I'm not very talented in drawing circles, but we should see broader lines, okay? Or lines that are further distance away from each other. Alright, and so obviously we have the magnetic fields with solenoids. Now if you have it going through the Y, we create a thing called electromagnet. Depending on the number of coils you use around this iron core, you can actually increase the amount of magnetic field strength you generate in that there. So that's the function of a solenoid. You'll see the actual application there is quite useful. Last one, I think this is. The question is, what is the right hand grip rule? Now, trying to use these two movements, try and work out which direction is the magnetic field going for both of these. So let's have a look. So for our first one here, our first example, that is, we have that is our magnetic field. Okay, so our magnetic field in this case is going in a anti-clockwise direction. Our thumb represents, or our current, sorry, so this is the current, direction of the current, and we want to work out what the direction of the magnetic field is. If you use your right hand grip rule, our thumb is pointing out the page in the center here. So it's coming out here, which means that the magnetic field, if you want to picture it, is coming out and then circling back to the other side. So out of the page here, and then going into the page on the sides, because it's trying to reach to the back of the other end of the circuit, which means that this would be the opposite. It's going into the page and then it's coming out the page in this case here, because it's coming towards you, so it's coming towards you, and then it's looping into the cylinder there. If we use this, so we're dealing with solenoids, so our fingers is the direction of the current. So in the first one, my fingers are curling down, my thumb is pointing to the right, so that's north, this is south, and then B here, you can see it's in the opposite direction, so we have north, we have a south here. Okay, so that's what we have. You can draw it out like that, nice and pretty with colors if you want. The last one we are going to do, it says label the magnetic poles for the magnet that would produce the magnetic field pattern shown below. So in this case here, remember it's always away from the pole if it is a north. So north here, and then south. So we're showing a north to south motion here. Draw a diagram of a solenoid which produces a magnetic field identical to that. Okay, so if we picture it using our right hand grip rule, our thumb is pointing in this direction. Using my fingers as example, we should expect that to generate such a magnetic field, our fingers need to be pointing down. Okay, so my solenoid that I have here, we have magnetic field lines coming along. So I might just, draw something along the lines of that. So it goes up, down, 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 and then staying down like so. So north and south. Right, so north to south there. This response here is actually incorrect, so the other way around. So that is north there, that is south there, and then you want your field lines going in the opposite direction. Alright, so summary of all these points here. Now, what we talked about is how to represent magnetic fields. We talked about, how the quantity of the magnetic fields dictates its strength. We also looked at the right-hand grip rule. So there was quite a lot of things to unpack today. So hopefully you were able to understand most of it. If not, feel free to watch the video again. And as always, stay safe. Hope you enjoyed the video. Give it a like. Encouragement boost is always nice. But anyways, enjoy the rest of your day.